we'll start today's lecture. So basically, we are into the ninth week of our uh, subject or course, and you know, uh, as initially at the start of the class, as it was told by professor, that this course will have two parts. Sorry, three parts. First was casting. Casting. Yeah. First one third was about the casting part that we discussed for four lectures. Then it was about the metal forming, various processes, etc. And this is the last one third part, which is about joining processes, mostly about welding, but there are other joining processes also, not only welding, but there are some more. Commonly, we permanent joining process, uh, but uh, there are some temporary joining processes or semi-permanent kind of joining processes, etc. So those are also there, and when we say welding, we primarily consider metals, and in that also we primarily consider steels because most of the metallic components which are practically used are made up of steels, various type of steels, not only mild steel, etc. But yeah, that's what we are dealing with predominantly. But today it will be the introduction for this joining processes topic. So from the content of the course of this week, you also would have gotten the same idea that you know uh, professor discussed about various classification of joining processes, then this heat affected zone, etc. Various kind of uh, zones that we observe within the heat affected zone, and how do they affect your uh, certain properties like ductility, toughness, etc. And then some heat treatment processes. So this is primarily part of metallurgy class, uh, where you discuss this iron carbide diagram first, and then various microstructures depending on certain carbon percentage in your iron and the temperature that you are talking about. You have an idea about uh, and depending on what cooling rate you follow during solidification, you can have certain idea that you'll end up with certain type of microstructures. Famous ones are perlite, bainite, martensite, gamma oxide is the liquid related one, or the it's like the starting of solidification, etc. So basics are covered in those courses. So we'll here briefly discuss some of the heat treatment processes because if you want to discuss them, you have to spend one whole class on that only. But that is not our primary purpose here. So we'll not do that extensively. And if you look at the assignment that you have for this week 9, there are not many numericals because this is like introduction class, so basic uh, stuff you're supposed to know about joining processes, and that's what we'll predominantly talk about today. And the main or the crux of the discussion will start from next week, where you discuss various type of welding processes one by one. So that will be more interesting or more uh, concept or the course wise more important ones. So this week we will try to do some basic stuff, etc. Okay. Actually, I'm having some cold and cough, so in between I'll be taking some water breaks. So bear with me. So yeah, we can start. So first thing is about the classification. So you have seen those tables in the class or the PDFs that are shared as class notes by professor. So you must have seen those that table where you have you know classification. So there are different ways to classify. Okay, it's not like whatever was told in the class is the only way to classify. There are different ways, and we'll see how to go about those. Okay, so you know, one second. Yeah, I'm just making sure my video is on because in one of the last classes it was by something it was not on. So yeah, video is also on, and with my video, I mean my screen is visible in the video. So you know, uh, yeah. So basically, there are different ways to classify. Mm, okay, so the the first topic of discussion is classification of joining processes. First criteria is you know permanent, semi-permanent, and so not much to discuss about this because the name itself is a you know describing what they are representing. So uh, permanent can be welding that we are going to study, and apart from that, one second, let me just check what all other categories are there. I mean, what are one second. Yeah. So welding is there, and as the name suggests, it is a permanent joint. You cannot remove it and use those parts again, so they will be permanently damaged if you try to reduce or reuse them. Predominantly, it's welding only. I'm just thinking, is there anything else? Because there are nowadays some non-conventional joining methods also, so you don't know. Some adhesive bonding techniques are there where you have, you know, uh, permanent setters kind of things, thermosetting adhesives. But permanent riveting is also there. You can say riveting is also permanent one because once you rivet, you cannot easily first of all remove those rivets, and if you do it, reusing those parts in that exact same condition is not that possible. Okay, so there could be others. I'm not saying only these two are there. So just for the sake of completion, I'm trying to give the wide range of applications. Semi-permanent, this could be brazing, soldering, etc. So what happens in these kind of brazing, soldering kind of uh, things, sometimes press fit, etc. You could have seen in most of the electronic components, this IC are connected with the wires using solder gun, and basically you use some low melting point temperature flux, which melts easily, and so that you have a metal to metal contact between the IC node and the wire end. But that is easily removable also. You could have seen that soldering, if some component goes bad, you just take it to the repairman and they will just remove the solder and again do it. So this soldering brazing, as long as you don't apply a lot of pressure or force, they will be kind of a permanent joints. But you can reuse those parts even after separating those joints. Okay. And temporary, so temporary means will threaded joints, and what else could be there? Rope, etc. could also be there. But as the name suggests, temporary means they will be designed for certain maximum force or load that they are supposed to uh, cater to, and then if that uh, they will basically separate out, and you can use those components again. It's not like that. So thread joints are there. Then there are like keys and slots. All those things are there. Uh, what else is there? Uh, yeah, I mean these are like the important ones. But this is not that important because the classification that is important, that is one set of it is discussed in the class, which is uh, what do you say this basically there are two more ways to classify. First is based on this autogeneous, homogeneous, heterogeneous. Okay, so one second, this. Okay, so second one is, maybe I should use this kind of tree diagram. So autogeneous, then you have homogeneous, and the third one will be heterogeneous. Okay, so this was also taught in the class. So basically autogeneous means no filler material. So when you have a joint, you have a single type of material throughout, no filler material, extra material that you use. And the most famous example of this kind of autogeneous processing is solid state welding, you know, solid state welding and resistance welding. We'll see what kind of methods are these and how they operate, etc., in the subsequent classes. So for the time being, just bear with me. Homogeneous means this filler material is same as the parent material. So by parent material, I mean the materials that are being welded. So when you weld same types of two materials using the filler, which is also of that same material, then it is called as homogeneous welding, uh, arc welding, gas welding, thermate, etc. So there are different types. We'll see, but there could be many also. Okay, and heterogeneous, it means filler material is different. So in the mathematics term, not equal to parent material. I mean, it's not strictly correct, but you understand, right? So these two materials will be different, and you have brazing, soldering, etc. into this category. Okay, so this is another classification. Then there is detailed one. Okay, so that was discussed in the class also, which is depending on the bond type. So you have whether you have mechanical bonding, atomic bonding, and then there were some sub classifications, etc. So maybe we could see that also. I'll not go into details because those details go and check because it was discussed in the class. But I'll just give you the whole summary so that you understand. So third category should be this: which type of bonding is used for the joining process. So you have broadly two categories, which is mechanical bonding. Another one is atomic bonding. Okay, so one second. Okay, so yeah, mechanical bonding and atomic bonding. This was done in the class, so I'll just briefly run through it. Temporary. In mechanical, there are certain categories. You know, uh, uh, maybe we should have some tree diagram so that if somebody wants to remember. Second, so yeah, mechanical. So you have temporary ones. So this one is similar to what we did in our first category, which was uh, threaded joints, etc. Then you have this permanent or semi-permanent. So let's talk about semi-permanent ones. So you know that is same as what we discussed. So I'm not discussing those again because this categorization we have already seen. We'll just focus on those who are new. Uh, you know this solid state. So okay, so I mean this permanent I should have written here only. Okay. And atomic bonding, you have solid state welding. Then there are like 3 4 categories under this: cold welding, friction welding, diffusion welding, hot forge welding. So those things we will see as much as the time permits. Then you have this fusion welding. Fusion basically implies there will be some liquid involved. So this arc welding, resistance welding, etc. Those fall under this category of electrical fusion. So this gas welding, oxyacetylene, etc. Those fall under this kind of fusion welding, thermate, etc. And then you have uh, solid and liquid state. So there will be separate, distinct solid plus liquid state welding. So the difference is in the solid state welding, this first category, there will be only solid state. In the fusion state, there will be mostly liquid melting kind of thing. But here you'll have both distinct phases, and that happens in your brazing, soldering, etc. So brazing, soldering, and third category is also there in this subclass, which is called as adhesive bonding. Usually, this is not discussed when we talk about uh, welding, etc. But adhesive bonding is also sometimes used as uh, this one. क्या बोलता है? Adhesive bonding, basically, as the name suggests, it's adhesive. So there are two kind of adhesives here. This one you should already know, thermoplast and thermosets, because these are different kind of plastics also. So thermoplastic adhesives, and you have thermosetting adhesives. So same, this definition is same as the polymer definition. It's just that these polymers are used as adhesives here. Okay. So thermosetting means once it is done, once it is settled, or once it is dried or cured, then you cannot reheat and melt it. Okay, so it's more stronger, but it's like a one-time thing. Thermoplastics, usually you can reuse it, assuming it's easy to do that in your structure, and their strength will be lesser. So the trade-off is there. Okay, and then there are some other welding processes like electron beam, etc., etc. Those we'll see. Those are called as more advanced or different type of methods. But there is last one more classification still remaining, is this one. So I'll just give, it sometimes helps, because what will happen in the next class, that we'll see so many uh, techniques that you will be overwhelmed as to what we are trying to do. Okay, so this classification is from that point of view, to remember which welding method comes under which category. Okay, so uh, this is like the which number we are going. Okay, fourth one, and this is based on the uh, type of uh, welding technique that falls under various categories. Okay, so first is a solid state. So here you will only have solid state present during welding or joining process. So you have different subcategories of processes. First is called as explosive processing, welding. Then you have something called as ultrasonic. Then you have friction, or friction stir welding is also called, but typically let's say friction. Then you'll have forge, and you'll have diffusion. So these five types of welding methods will only involve solid state. There won't be any liquid or any gas. Then you have a liquid state, or this is also called as fusion. So here some melting is involved. So there are three broad categories. You have arc welding, then you have resistance welding. The third category is chemical. Okay. So arc has three subcategories. First is flux. Flux cold, or flux coated, I think. Then you'll have shielded gas. Shielded gas. Oh, the spelling is wrong. And then you'll have submerged arc. Okay. Shielded arc has three more subcategories. TIG, MIG. What are these? These are like famous methods. Resistance does not have any subcategories. Chemical reactions, there are two types. First is called as thermate, where you have exothermic reactions. And then you have gas, so basically like torch, oxyacetylene flame, etc. Those things. And third category is solid plus liquid. So I think we already discussed this one. Basic and soldering are uh, prime or main categories under this. So this is a classification based on the types of methods. Okay, so Depending on what you are comfortable with, you can remember the whichever is the easier one to remember. These are all memory maps, so that you should be able to you know keep track of things what is happening. Because you'll study different techniques of melting, etc. And these are like the conventional ones. Okay, so there are newer ones or unconventional ones. Usually what happens using these conventional methods, whenever you do welding, you will have a significant heat affected zone, which is not desirable in many applications. Many sensitive applications require homogeneous properties throughout your domain. Very energy intensive but very short area kind of welding processes, which are typically achieved using lasers. Okay, so this laser beam welding, electron beam welding, these are you know these are methods which are out of all these classifications. Okay, but they are very important because they have very small heat affected zone, and you know you have very better, or you have improved control over the welding, etc. But you cannot apply them everywhere. You cannot weld big components using laser beam, etc. That will be very inconvenient. If you want to, you can, but typically they have niche applications. Then this is mostly about metals. Then there is some plastics. So plastics typically don't have that much thermal strength as the metals. So there they have some unique welding processes, etc. Those were discussed in the class. So I'm not going there again because it will be again the repetition. So then this is about the classification, and then professor talked about something called as I'm just trying to discuss, because otherwise this is all uh, theory class. So there was discussion about the efficiency of the welding, right? So efficiency of welding processes or welding process, any typical welding, because later on you'll see for this electric arc welding, etc. You have for individual methods also you can define the efficiency, but here we are talking about general general welding process. So there is a simple formula for that. Let me just look into it. MIG is metal inert gas welding, TIG is tungsten inert, POW is plasma arc welding. Okay, so those things we'll discuss later. Yeah, so melting efficiency or welding efficiency. One second. Oh, okay. One second. There is a slight this thing here. Yeah. So, okay. what happens, there are two efficiencies here. So when you say efficiency of welding process, there is one efficiency which is like you have some heat source, right? So you have some heat source. So from that heat source, you get some heat output at your welding station or setup. So there will be some losses there. So one part of uh, this thing goes out in that, which is called as sometimes they call it as transfer losses, okay, or something like that. Let me just see the name. That's what I'm looking for. What is the exact name? Yeah. So let's say from heat source you took Q watts of heat or joules of heat, but what will happen? You will receive HS amount of heat at the working station or welding station, and that will be some efficiency, let's say, or efficiency 1 into Q. This is called as heat transfer efficiency, because uh, there will be atmospheric losses, right? Significant losses happen because welding is not a very sensitively controlled process as far as heat transfer is concerned. And then out of that heat, so this HS is uh, heat available for welding, actual. Okay. And then what happens? Then when you do the welding, basically melting is happening. So then you need HM, which is uh, sorry, energy required for melting, right? So in welding, actually melting is happening. So this HM is energy required for melting, which will be MCP delta T plus M into L. So L is your latent heat of uh, uh, fusion or melting. So ideally speaking, HM should be equal to HS, but in reality, there will be certain thermal losses to the surroundings also during melting process. So this, you define one efficiency of melting in these cases, which is nothing but what is the actual requirement upon what you supplied. Okay, so this is how it goes, and you have to always be careful about uh, units here, because many times units are uh, sometimes instead of joules they will give you in watts, so that is joule per second, or sometimes just to confuse students they give in joule per mm. Okay, so per unit length also they mention sometimes, so you have to be careful. Okay, so that is there. So now let's take one problem about this, and we'll see how to tackle these kind of questions, because to be honest with you, I could not find any other numericals to discuss on today's class. So okay, so let me just see. Okay, so uh, let's take this question. 900 mm long steel plate is welded using heat source, or they have not mentioned heat source, they have just mentioned using source which which is at 150 ampere currents, 20 volts DC, and welding speed. Okay, so maybe I'll write that. Or 1 second, welding speed I'll write separately because they are just talking about the heat source here. Okay, so they have given this information about the heat source. Speed is 300 mm per minute. So basically in 3 minutes you are doing one complete length of the weld, and process efficiency is 80%. Then find the actual heat supplied for welding. Okay, so now basically they are asking about HS. Okay, so we know, this Q, I'm talking about this Q. Q you can calculate V into I because this is electrical heat source. Voltage into current, if you do, you'll get 150 into 20, 3000. Correct, no? Because IV is generally in watts. But now, see here you can, I mean, as I told you, usually they, if they had given options in Q into this efficiency, right? So 80% is 0.8 times. So this will be 0.8 into 3000 will be 2400 watts. So okay, so if 2400 watts is given in the option, you can tick it. But usually they will not give that because of this new thing, which is uh, uh, welding speed, etc. So here you have to be slightly careful because the options will be, they will mention like find in joule per mm. So in that case, you cannot give this as answer because this is joule per second, right? What is joule per second? They want answer in joule per mm. So basically, if you multiply this by some second by mm, then you'll get right. So this will become, uh, I mean, I hope you get the idea what I'm trying to say. 400 watts is the answer, but the options will not have that. They will have joule per mm. So in that case, no need to worry. You have to just divide by the velocity. So HS can be, efficiency into VI divided by the velocity. Okay, so this 2400 we already have calculated. So if you divide, so this is 300 mm per minute. So per second it will be 300 by 60 mm per second. This is basically joule per second. So this is 5. So 2400 divided by 5. So that will be 48, and 10 will come. So 480 per 48 into joule per 480 joule per mm. Okay, so sometimes they try to trick uh, uh, students using these kind of things. Okay. Okay, so there was one more question. Yeah, other questions are, mostly like they are particular for some processes. So, that's why I said it's very difficult to find numericals today. Anyway, let me see one more thing. If not, then we'll discuss theory only. Mm, yeah, so this can be one more question. So basically, this is related to something called as spot welding, but you can treat it as a general welding thing. So what is happening is there are two 1 mm. Okay, so this is their thickness is 1 mm. There are two such sheets, and they are being welded together. Okay, their density is given as 800 kg per 8000 kg per meter cube. So mostly steel or iron. Yeah, mostly steel because 7900 is there. Okay, and what is happening when they are welded? This gap when it is welded, it is becoming like a circle. Okay, so it's the weld gap after solidification. It is becoming like a circle of diameter 5 mm. Okay, 1 second. So basically, what is happening here is actually the question is not that clear what they are trying to infer from this. 125. Maybe I'm looking at the wrong question. 1 second. Okay, okay. Yeah, yeah. So sorry for this. This is actually this is for some other question. So my apologies. Here the question is quite straightforward. What they're saying is, you know, this is your welding zone. Basically, they are welding two sheets. So the, let's say, this cross sectional area for this weld zone, this is your weld zone, is A, and you are traversing, so your welding speed is V. Okay. So V is your welding speed, A is your cross sectional area, of your welded zone, and they have given that it is a circular cross sectional area. Okay, so you can assume it as a circle. But what is happening in this weld zone? Basically, what is happening? There is one wire roll which is coming here and then melting, and this zone is getting filled by this melted wire, and then it solidifies. Okay, so like that it is happening. So, and for this wire, they have given that this diameter of this wire is 1.2 mm, small wire. Feed rate of this wire, so at what rate this wire is being fed to the welding process, is 4 meter per minute. Okay. And here you are supplying some uh, heat source is there. Okay, because this wire will not melt on its own, you have to supply some heat source. So that heat source is nothing but 200 ampere current and 25 volts. So basically it is again electrical heat source which is providing the heat for melting and welding. And this welding speed is given as 18 centimeter per minute. Okay, and they have given this heat transfer efficiency, which is we are calling as efficiency 1, as 65. So you need to find first, you need to find two things. First is actual heat supplied. So basically HS is what in kilojoule per mm. Okay, so again here it is not kilowatt, so life is not that straightforward. And second, you need to find this cross-sectional area of your welded zone, or let's say diameter of your welded zone. So assuming it looks something like this, so it will have some dia d. So this, what is this diameter d in mm? So this is a two-part question. Okay, so this is the direction of this wire feed. It is going into the weld pool and welding. Okay, so this is how the setup looks. They have mentioned which kind of welding process is there, but I'm not specifying that because we have not discussed those things. See, first part we could, we have just done such thing. So HS is nothing but into V into I divided by the welding speed. So here it is 65, so 0.65, 200 amperes into 25 volt DC divided by welding speed is, now it is centimeters, so we'll convert everything into standard units, but they are asking in mm, no? So let's convert this in mm. So 18 centimeter is 180 mm, and this is minute. So this will be joule per second, and this will be mm per second. Yeah, so second goes away, and you will get answer in joule per second. So clearly this becomes 3. So if you do the calculations, the numerator will be 5000 into 65, sorry, 0.65, so that will be 15 to 65, so that will be 15 to 65 divided by 3. So we will have 1083.33 joule per mm, but they are asking in kilojoule, so this will be 1.083 kilojoule per mm. Okay, you have to be very careful if you are thinking of GATE exam or something like that. Always be aware of units. And second problem, second part is this one. So here you have to apply mass conservation principle, because whatever is the volume of wire that is coming into you know uh, mass of wire coming in through the feed for welding, it has to be equal to mass of the wire, mass of the weld pool. Should not be mass of the weld pool, increase in the mass of the weld pool. Per unit time. So these all quantities are per unit time basis, right? Because this process is time. So basically steady state kind of thing is happening. So therefore you can write and this is also additional mass. So in whatever, let's say in 1 second, whatever wire mass is coming, that has to be get melted, right? So then only this process will make sense. So then you have pi by 4. See, density of wire, let's say rho, then mass is density into volume. So volume will be area into velocity. So this is for wire, and then you have to multiply by feed rate of wire. This has to be equal to density into, we assume that wire and plate are of same density. If given in the problem, okay. If not, then you have to assume. Then this is the cross sectional area for your uh, weld pool, this circular cross sectional area, and it is traversing with velocity v. The density goes away. If they have mentioned that the densities are different, etc., then you have to use. But here nothing mentioned, so you can forget about those. So then you can solve this d square, right? So 1.2 mm. Let's keep it in mm only, so that you'll get area in mm. Feed rate is 4 meter per minute. So 4 by 60 meter per second. And this is area, let it be. Velocity is given as 18 centimeter per minute. Okay, so 180, 18 centimeter, no? So this will be 0.18 meter per minute. So per second. So 60 goes away. So area, you can calculate this. This 4 gets cancelled. So basically pi into 1.44 divided by 0.18. So what will be this value? Pi into 1.44 divided by 0.18. So area comes out to be, the cross sectional area of the weld pool, 25.133 mm square. Okay. And then one can calculate the cross sectional area. So you have to just equate it by pi by 4 capital D square, no? So you have to just multiply by 4 divided by pi and then take the square root. Okay, so this capital D is 5.657 mm. Okay, so this is how we solve these kind of problems. since there was a discussion on efficiency, I thought we'll take certain problems. So there are other problems, but as I said, it needs more knowledge of that particular welding process, which we will have after maybe next class or by the end of next week. Okay, so this is about the numericals that I could find for today. Apart from that, okay, so then let's move on. So classification is done. So the next one is then there was discussion on this efficiency of heat source, etc. So we discussed about the efficiency part for a general welding process. Then it becomes more like involved discussion particular to that process. But you should understand one thing, uh, you know, if there are less losses, that welding process will be more efficient. Okay. So, for example, what happens in some welding processes, you maintain inert atmosphere about around that uh, area, welding area. So, in that case, there will be lesser losses to the ambient, and you will have, you know, uh, higher efficiency of melting or welding. Okay. So those kind of things are there. Uh, there was one problem on this melting. I'm not able to find it. Let me just search it again, because it was asked in one of the previous GATE exams. I may not have it with me. Yeah, it's not here. Anyway, it's fine. Let's move on. But the idea is same. You can solve. You have to solve using the same method. You have to find the total energy, efficiency, then actual melting. So as far as I remember, in that question they had asked the next part also. That's this HM. So far we have only saw HS. So they have asked for HM also. That is the next part, which is expected. I'm just looking for that question. If I'm able to find, that will be better. Yeah, I found it, but it's a different variety of question. Yeah, maybe later, because it is slightly different. Okay. So then there was discussion on this, you know, heat affected zone, etc. So you should understand one thing here, that this welding process, it is permanent joint, that is fine, but this will always introduce anisotropy in your material at the weld zone, because when you are welding something, you are increasing the temperature of that local part above the melting point of that particular material, if it is a fusion welding, or otherwise that filler is at least melted. So if that filler is I mean, mostly we deal about fusion weldings, because that is the 90% of the welding is arc welding, which is fusion welding. So there what happens, it's a very complicated process to analyze. I mean, we study this like, uh, I mean, we don't actually study what is welding, we just study upper se. So we just study from our uh, for our understanding basis. But if in reality, if you want to study this, it's very difficult. I know my one of my friends who's actually working on this. So first thing is, you have to understand the processes that are taking place. First, you have external heat source, which is very local. It's not a body heat source or surface heat source. It's a almost a point heat source if you have big specimens, and if you have lasers, that point is even smaller. Okay, so that is first thing. And uh, your workpiece moves, or if your your workpiece is steady, your electrodes or the welding tool moves in one direction, right? But when you study welding processes, what you assume the electrode to be stationary and your workpiece is moving in the negative direction. So basically you do the change of frame of reference kind of stuff. Why you do that? Because when you sit at the tip of the electrode, I mean, you can't sit there, it will be very hot, but assuming that you are able to sit there, you will observe around yourselves that material is coming from one direction, melting exactly at the bottom of your electrode, and then leaving the electrode. Okay, so like that. So by doing change of frame of reference, by selecting the frame of reference as the observer standing or sitting at the tip of the electrode, you solve that relative motion wala problem. Okay, that is fine. But see, if it is a fusion welding, there will be uh, two phases, right? Liquid and solid, and in between there will be the bushy zone, because uh, in most cases the solidification and the uh, I mean liquid gets solidified. There will be bushy zone in many cases, because you typically deal with alloys. You generally don't deal with pure metals in reality. Okay, so what happens? The solubility of particular alloy element in liquid of the other metal is different than in the solid. Okay, so that is why. So it's very difficult. Plus, there are certain effects like Berengueri convection, radiation heat transfer from the melting pool to the surroundings. Uh, and the deformation that takes place in the workpiece, which is not actually undergoing the welding process because of high heat transfer. Because you should understand, it's a very localized melting process, but the heat transfer will take place within the body of the workpiece. It will not melt as a whole, but there will be temperature changes. Okay, that is why this heat affected zone comes into picture. I hope you understand the background of this, because otherwise when you prepare for gate exam, etc., we don't pay that much attention to what actually is happening there. It is very difficult to simulate these kind of processes. Okay? It's not that easy. People do it by, okay, what happened? What did I do? Okay. yeah, with that background, let's start this heat affected zone discussion. So it is again more of a theory part only. Okay. So this famous diagram is there given in the class. Let me just try one thing. 1 second. Yeah, so this heat affected zone, uh, there are different layers in it. You must have seen in the class only. This figure was uh, 1 second. I just thought. Uh, yeah, right. I'll just copy that image. Just check it once. Okay. Mm, So here, I mean, this was discussed in the class, but I'll just highlight some important points. Uh, so see, you see this part, right? Okay, 1 second. Yeah. So this part, this is your actual alloy formation. If you are filler, 1 second. Screen is shared, right? Yeah. Why am I not visible? 1 second. Okay. So here you have, if your filler material is different from your parent material, you will have alloy formation after solidification. So that will have different properties. This yellow boundary is nothing but the boundary between the uh, weld bead or weld pool and the remaining material which did not undergo welding. Then you'll have this grain growth zone where you'll have basically here you'll have coarse grains. Okay, because this part remains hotter for a lot more time than the other parts. Here you'll have crystallization zone and you'll have finer grains here. Okay, so as you go away from the uh, welding metal welded metal area, your grain size typically goes down. Okay, so there is one figure also about this. Let me just, yeah, okay. So sometimes, yeah, worse than, yeah. So as you go away, from fusion to HSZ. Okay, and then you have these other zones where partially transformation, tempered, etc. That you understand, right? Because this red line, this is actually your temperature. Red line that is showed here. Uh, because everything happens because of temperature. And as you go away from the bead and etc., there will be lesser temperature and not much happens there. Okay, so this is one thing, and sometimes you want to reduce this heat affected zone. So this is called as heat effect, and this is called as fusion zone where actual melting and all those things take place. So you want this heat affected zone to be as small as possible, right? Because otherwise there will be, if it is too big, then there will be larger, you know, uh, more anisotropy in your welded part. So you don't want that. And one more thing is this anisotropy is also invitation for corrosion, etc. Okay, so you'll see this corrosion, etc. It starts mostly at the grain boundaries, and if you have different types of grains, the corrosion is also very prominent on those things. Okay, so for welded joints, corrosion is the one of the uh, biggest enemies also. Okay, and then there is very famous uh, this thing about this fusion zone. So if you look at the interface, this yellow line, that very famous word is there. Let me just see once. Epitaxial growth. Okay, so what is it? Basically, within this fusion zone, if you uh, I mean, at the boundary of fusion zone and base metal or parent metal. The growth of your materials is it's very weird. Okay, so let me just see if I can find any good image about this, because this epitaxial word is used only here. I'm just trying to find a good epitaxial growth image. Otherwise, I'll have to draw it. Yeah, maybe this image will be better. Okay. Okay, so I have epitaxial solidification. Okay, so you can remember this word for your competitive exam. Let me just oh, it is some ppm file. 1 second. Okay. Okay. Yeah, now it should be fine. Yeah. So this is solidification grade boundary. Okay. So what happens? As you can see, uh, you know, this is your welding direction, right? So if you see, this is your welding direction. So as you go along, this melt pool starts to solidify, right? But this epitaxial solidification, it means that the solidification starts from, or the dendrite solidification, dendrite start growing from uh, unmelted parent material. So you can see this base metal that they're calling is also called as parent metal. Okay, so this dendritic growth starts from these because they act as a nucleation sites, and then you'll see this is not a particular category of dendrites that we have seen so far, and this is at any t. Okay, so this is for any time t. So okay, so what happens as time goes, this picture will keep on changing. Okay, so you have to understand that, and you have to uh, keep an eye on this dendrite. So they are not like columnar or equiaxed or whatever we have seen so far, and that is why they have given a special name which is called as epitaxial solidification. Okay. You can see some YouTube videos also about this. You will be, if you don't understand how, but this is particular to our welding process. Okay, and what happens? The growth starts from the unmelted part, but then there is a competitive growth of dendrites. Okay, so in this region, there is a competitive growth of dendrites. Okay, so epitaxial solidification is also there, and then you have competitive growth. So therefore, you will not have any uh, homogeneous or good looking structure. It will be like that Amazon forest kind of thing. So to get the sunlight, the trees will compete with each other. Similar to that, here also the dendritic growth will be competitive. Okay. And then this final topic about heat treatments, etc. So as I said, heat treatment is again, you know, yeah. And one more thing about this heat affected zone before we close it. So as you know, the temperature is different in different regions. The microstructure will also be different. Okay, so it's not only the grain size, the constitution of your grains also will change depending on how for how long you have kept that zone at that particular temperature. Okay, so for that you have to refer back to the equilibrium diagrams for this corresponding parent metal or parent material. Okay, so that is also there. And yeah, then I think, yeah, then you can see for iron carbide, etc. How do you define those things? All those things are there. Yeah, I mean, as I said, this heat affected zone should not be large because it reduces toughness and it is the invitation for corrosion. Okay, so that's why many times laser welding is preferred for critical applications such as satellites, etc. In those cases, you don't do normal arc welding mostly because of these things. You usually prefer laser welding. Okay, so cost is more, but the sensitivity of application is also important there. And then there is discussion about this various heat treatment processes. So let me just see one thing. Mm, I just want to give you a you know flow chart so that you can remember, because there are a lot of heat treatment processes also. And again, this is the core part of your materials subject, not our subject, but still since we are here, we should give it some due diligence. So let me just see if I can get some better flow charts. Okay, one second. Yeah, one second. Okay. There are a lot of these things. Yeah. Okay. So maybe this one is better. So heat treatment process. Okay. Let me just do one thing. Can I just borrow this image from internet? Let me just check once. Yeah, I think it should be fine. One second. Okay. Yeah, because in the class that one slide is given, right, but that slide is slightly confusing because all the processes are listed down just one below other, but they are actually, yeah. Why is it not here yet? So I have to download. Yeah. So these are the main heat treatment processes. You have bulk heat treatment processes, then you have surface heat treatment processes. In bulk heat treatment processes, you have annealing, normalizing, hardening, tempering. All those things are there. Uh, Annealing has next four categories. Then tempering also has Mark tempering, Gauss tempering. And there are some surface heat treatments also, because in many applications you need uh, desired properties for certain surfaces. So you know, maybe this is blur. So I'll just, I don't know whether this is helping or making things worse, but whatever it is, let it be. Okay, so if you remember like this, then it will be easy to remember. But because otherwise in the class it is all given in a list format, that is not helpful much. Okay. Okay. So then what happens? See, annealing and all this bulk treatment processes, uh, they basically are done to reduce the uh, residual stresses in the bulk of the component, as well as to increase sometimes ductility, etc. Those things are done. And what is annealing, normalizing? I think professor has explained those things in the class. You can also look it up. But annealing is basically you heat it till its upper critical temperature. If we are talking in terms of iron carbide diagram, because mostly we are talking about mild steels here, because see, high carbon steels are not easily weldable, and so therefore we have only some mild steels, etc., medium steels that can be weldable. So in that context, we talk about upper critical temperatures, and annealing is you heat it up to that temperature, and then you leave. I mean, you maintain the temperature for certain time, and then you leave the component in the furnace itself. So then you'll get a certain your cooling rate will be very slow, so you'll get coarse perlite structure. So that is annealing. I think the normalizing is you basically air cool it instead of furnace cool. You air cool it, and you get fine perlite or rate of air. This hardening and tempering, I think you have higher cooling rates because you may not want that much increase in the ductility or grain size because that will reduce your hardness. So you increase the cooling rate, you have higher cooling rates, but in that case also you need to relieve the stresses. So you do different kind of things. Those come under mar tempering, gauss tempering, etc. Okay. Okay. So and that surface hardening, you understand, right? Basically, you make the surface hard by uh, heating it and then rapidly cool it. So your bulk may not be that tough or hard, but your surface is very hard. That is usually required in some tools or instruments like knives, etc. Edges need to be hard, etc. So, and thermal surface treatment is not always desirable or feasible. So in those cases, you go for different things. Like carburizing, nitriding, cyaniding, thermochemical surfacing treatments. And then I'll give you this TTT diagram or C curve also it is called. Else, but since we are here, I'll just give you that image so that you'll remember what we are talking about. One more image only, and then we'll maybe stop for the day. So just one more time, because this is all theory. If you want, you can revise it on your own also. But yeah, not big scope for problems today. Okay, so these all images are from internet only. You can also look for them. Maybe I'll put it on the new page only. Yeah. So now you see here, this is basically your uh, effect of cooling rates on the final grain structure. Okay, so you see here the yellow line which is at the top, that is your annealing basically. So I'll just use those colors so that you may be able to correlate them later. So this process is basically annealing, because you see the cooling rate is very slow because you are cooling it in furnace. And see this these two C curves, they are the start of your uh, formation of your what do you say, from gamma or austenite to perlite. Okay, so you'll get coarse perlite at the end of annealing. And when you do normalizing, this is your normalizing, this part, this light. And depending on how you, what is your cooling rate, etc., get fine perlite or upper bainite, etc. Mostly you'll get perlite only, because usually bainite, etc., are hardened perlitic structures. Then next is Aus tempering. So this line, uh, yeah, I think maybe this would. So this is your Aus tempering basically process. So you maintain your cooling rate such that you have a higher cooling rate, and then you maintain constant cooling rate. It's not like constant cooling rate all the time. So that is called as Aus tempering. And in Mar tempering, this purple one. So this is your Mar tempering. So it just depends on the cooling rate that you adopt. And then oil quenching and water quenching are there. So they will obviously give you martensite. Okay. Aus tempering will give you bainite at the end. Tempering will give you martensite at the end. And quenching will also give you martensite, but the residual stresses will be higher in quenching. Okay. So people usually do some little uh, uh, heat treatment processes after quenching also. Okay, so this is like the broader idea. Today I thought I'll explain more with the help of images, because otherwise the theory becomes very boring, and you have to revise those things. Uh, and I hope you would have done it, because this was taught in the class also. Okay, so with this we'll stop for the day, and maybe next time there will be some scope for problems. Let me just see the syllabus of next time and the assignment. Yeah, next time it will be more point, up to point, not like a general discussion. Okay, so with that we'll stop, and yeah, see you next time.